take a look at number 2 first, since a lot of us kind of forget about these types of exponents. So the question is, 25 to what power is equal to 5? And what did we come up with, Josh? Right, 1/2 power, because the 1/2 power says take the square root of 25, and it tells you to take the positive square root of 25. That's what that exponent means. Okay. Another way to look at this, and you'd say, well, why would I do that? Just like if you had a really like huge number there, and it was like a 5th root raised to the 3rd power to get the answer, and you like didn't know it off the top of your head like this. This is a strategy you could use to find the answer with something that you know how to do. So this is what we call an exponential equation. You're trying to solve this exponential equation. You're trying to solve it like the minute I take that question mark out and I make an x there, you're trying to solve this equation for x. So anytime you can write, and this 5 right here has a 1 for a power on it. So anytime you can represent both the left side of your equation and the right side of your equation with the same base, then you rewrite both sides with the same base. For example, the base on the right side right here is base 5, and the power is 1. So if you can represent 25 as 5 to some power, which you can, and again, like I said, we wouldn't do it for this because a lot of people can do it in their heads, or with a little review of fractional exponents, they can do it. But again, these would be for more like nastier kinds of equations. So you look at that and you say, okay, to solve for x, I have to use my exponent powers here. And when I have a power raised to another power, I multiply these. So I get 5 to the 2x equals 5 to the 1st. So now to solve for x, since your bases are the same, all you have to do is solve that equation. 2x equals 1, x is 1/2. So like I say, even though we wouldn't bother doing it here, sometimes you can get exponential equations where you can't just look at it and know what the rational exponent is, the fractional exponent. Now, what's the problem with this? It's going back a few weeks here now to finding the inverses for a function. We use this strategy called switch and solve, which is you switch your exponents here. You switch your variables. And then you're supposed to solve this for y. So what's the problem we run into here trying to solve that for y? Yeah, how do you do it? Y is the exponent. X to the y, you can't do x to the y. That doesn't make any sense. Our goal here is to have y equal something. Okay, and we can't do it. We don't have a strategy because we don't know how to do the inverse of an exponential. Because every time we found inverse functions, we knew how, if we were multiplying by a number, we knew what to do, we divide. If we were adding something, we would subtract. We knew how to undo. If we were squaring something, we would square root it. So we knew how to undo different things, functions we had seen previous to this. We don't know how to undo an exponential function. So the first question that rises is, does an exponential function even have an inverse? We'll look at that in a minute. We'll look at it graphically to determine if it has an inverse. Now, I know it's hard enough to go back to last Monday and expect you to remember exponential functions, never mind inverse functions, which we did. How far back was inverse functions? Let's see. Whoa, way back on October 21st and 23rd. That's a month ago. So we'll do a little review, and that reminds me that the only thing we have to do to adjust our schedule, since we missed class on Wednesday, is everything's just going down one day. So today, Monday, we're doing what we would have done last Wednesday. This Wednesday, we're doing what we would have done today. And instead of having an in-class quiz here, we'll do it as a take-home. So that's how we can adjust. Yep. John, is that just stretching?
Yes.
Oh, okay. Okay, good. I'm glad you like take-homes. All right, so let's start us off here, Eli, with a brief summary about inverse functions, part A. Let's see. Let's see if these exponential functions pass that we have graphed right here pass a horizontal line test. Let's apply 1a to it. Well, whether we use the exponential growth function or whether we use the decay function, we can see that if we pass any horizontal line anywhere through these graphs, it touches function, the graph of the function, in one and only one spot. So both of these pass a horizontal line test. So we know that there is something that exists called F inverse of X and G inverse of X. We don't know what it is yet, but we know it exists. Okay, so we know it has an inverse because it passes the horizontal line test. All right. B, Mackenzie? C. Part B says, well, let's see, f of x looks like this. And if I put an x in like this, let's say I put the x value in 3, what comes out? 2 to the third? That's f of 3? 8. So it says I can put the output into my inverse function, and I come right back to my original. There's my round trip idea. But I don't still know what that inverse is. I know this will happen, that if I did a picture of like function machines, because I know how inverses work, that if I put 3 into f, out comes 8, which is 2 to the third. And then if I take that 8 and dump it into whatever f inverse is, I'm going to come right back to 3 again. But I still don't know what to call f inverse. So, but that's what they're talking about there. Okay, C. Paul? Paul? So we learned that you can swap the domain and range around with inverses. So let's take a look at just a little quick review. What's the domain of f here? What's the domain of this function and what's the range? Domain of f, range of f. D, please. Okay, so that's how we found the inverses. Some of us used the mirror in class. Some of us actually drew the line in and just reversed the coordinates, the x and y coordinates. So we would put our line y equals x in here, like that. And then we would reverse the coordinates. So if we had the y-intercept here, 0, 1, whatever our inverse function is, what point must lie on our inverse function? 1, 0. Right. You just reverse it. And notice those 2 points have the same distance about the line y equals 1. And we could just, I don't want to do it because it's going to be what we do in a few minutes, but we could just take a bunch of points on 2 to the x, reverse the coordinates, and we could actually get a sketch of the inverse function. That's coming up. All right, and then finally E. And the 3's cancel, the 2's cancel, and you come back to x. And when you reverse the order, so now we're going to take f of x, and f of x, which is this function, will be the input. We'll go right in there to our inverse function. 3x plus 2 is f of x. Take away 2 over 3 brings us right back to x. So when we compose our functions, we come back to our original input. In both of these situations, the original input, look all the way inside, is x. Notice what your answer is, x. Okay, so that's a quick review of exponential functions. So because these exponential functions, whether we have a growth function or a decay function, pass the horizontal line test, we know both of these have an inverse function. All right, so let's take a look. I said we would be doing it in a few minutes. Let's take a look at how we would actually just sketch. We're going to just do a quick sketch of the inverse function by swapping the x and y coordinates. So here's x and f of x. And now we're going to take our f of x. will become the input. So this is F and this is F inverse. And then we should come right back to X, hopefully. So let's start with an easy one, 0. F of X equals 2 to the 0. That gives me 1. And here it is right here, that point we know for any exponential function that is not being transformed in any way, just your vanilla function, some number to the X, right? It's not being vertically stretched or shrunk. It's not doing anything horizontally, no shifts going on. We'll always go through that point 0, 1. And the other really important point to identify what the base is, what is the base of your exponent, is to say, well, its identity is known the first time you put a 1 here, because if you put a 1 in for X, then the answer is the base. So you go over here to X equals 1 and you go up and you're at 2. And that helps you identify what the base of your exponential function is. So those are two very important points to tell you what the original equation would look like. So if I didn't give you the function, those are the 2 points you look at to know, number one, that it's a straight exponential, and then to find the base, you look at the output for X equals 1. So over here, you put 0 into your function, out comes 1. Now you're taking 1 and you're putting it into the inverse function, and you're going to come back to 0. When I put 1 in, I get a 2. I put the 2 in, I come right back to 1, whatever this inverse function happens to be. If I was 2, I'd be 4. 2 is 4 right here. 2, 4. I put my 4 in, I come back to 2. 3 is 8. Put my 8 in, I come back to 3. Notice you end up exactly where you began. Let's take a look at some negative values for X. Negative 1, 2 to the negative 1 is 1 over 2. So that's 1/2. So now you put 1/2 into this inverse function, you'd come back to negative 1. You put a negative 2 into your original function. 2 to the negative 2 is 1 over 2 squared, which is 1/4. Put 1/4 in here, you get negative 2. And as X gets smaller and smaller as it works towards negative infinity, this graph gets, the output gets teenier and teenier, and it gets close to 0, but it would never be 0. So that's why, notice this is the range of 2 to the X, all non-negative numbers. The range of 2 to the X becomes the domain of the inverse function, right? And then look at your output for your inverse function, any real number. It could be a fraction, it could be a negative number, okay? Anything you want. So let's reverse these now. Let's actually plot these points right here on our graph, and we'll get a picture of our inverse. So let's see. A quarter is X and a negative 2 is Y. So I go a quarter and negative 2. I'm really close to the Y-axis. There I am. 1/4 negative 2. A half negative 1's right in the middle. Close. Nope. It's hard with this thing. Let me see if I can move it over just a bit. That there, and that there. There we go. And then 1 is 0. So notice on your exponential function, you have a y-intercept, and your corresponding point on your inverse function is the x-intercept, 1, 0. And now you have 2, 1 instead of 1, 2. So 2, 1. And instead of 2, 4, you go 4, 2. And instead of 3, 8, you'd go 8, 3. And life is good. So this function basically hugs the y-axis. It can never be 0 as an input. And it continues to grow, but very, very slowly. Very slowly. Okay? As opposed to your exponential function, which starts growing really, really slowly. Not too much going on. And then you get, when your output gets to be a certain number, and you double it, up it goes. This one starts off really quickly. Look, it's almost a vertical line. It's very steep slope here. If you took any 2 points, it's not a constant slope. And then it then slowly grows from there. Okay, so exponential growth, this type of growth really slow after a certain point. Still increasing, but the rate of increase is slowing down. All right. So that's what it looks like. We still don't have a name for it. We're just calling it the inverse of 2 to the x right now. All right, we already saw that we have a problem when we try to undo that exponential. We don't know how to undo it. We don't know how to get that x out of the air, so to speak. So the only way we can undo it is with something called log. A log is the inverse of a log function is an inverse of an exponential function. So they are inverses of each other. So if you have 2 to the, well, let's write 2 to the y here, its inverse is log, and so you know what exponential function you are the inverse of. Whatever the base is here is the base on your log. It's a little subscript. It's like a half a line below it. So that tells you you're the inverse of 2 to some power. And then you just put the y there. Okay. I don't like this. 2 to the y. Okay, I see what. All right. So let's take a look at it down here. So this is how you write the inverse of, if f of x is 2 to the x, then its inverse function looks like this. It's not a simple operation like adding and subtracting, multiplying and dividing. Whenever you see this, you say, I'm undoing an exponential function that has 2 as its base. Okay, it's its inverse. So if you put them together, and we waited until the class activities to do this, but what would this look like? I'm going to try it with all of you. What would that composition look like right now if I tried to write that? What is the input into F inverse? What is the input? What's my inside function? F of x, which is what? 2 to the x. Yep. So F of x is 2 to the x. Now I go to my F inverse. My F inverse function says take log base 2 of whatever my input is. My input sits right here. That's where my input sits. Here's x, here's my input. So now I put my input in. My input happens to be 2 to the x. And anytime I compose a log function and an exponential function with the same base, they're inverses of each other, they undo each other, what must my result be? No? X, what you started with. You come right back, you just lift off the exponent, just like that. Because you've composed a function with its inverse, you come back to your original. Now, you really want to blow your mind, do it this way. This is really weird. It's going to come up in a minute. F of F inverse of x. This is really funky to look at. What's F inverse of x look like? Log base 2 of x. That's my input. Where does the input go in on my F function? My input is where? Where's my input located on my F function? Where's my input go? Swap in the exponent. So I put all of this in. Look at how funky this thing looks. When you compose 2 inverse functions, what do you come back to? X. Voila. Voila. So it's a little weird to look at, but all you're doing is you're composing 2 functions. That's it. All right. So this statement right here is the one you're going to want to hold on to. Y equals log b of x is exactly the same equation as b to the y equals x. Okay, exactly the same. So let's look at these for just a minute. Let's start with the exponential for a minute. The base of the exponential is b. The base of your log is b. They always have to match. The exponent of your exponential function, in this case, is y. It's just what we're using here, y. Okay? The answer to a log is always the exponent. So simply said, a log is an exponent. Because remember, we're trying to get a hold of that exponent. We're trying to undo it. The output for your exponential function, the answer, becomes the input of your log. You're just switching roles with your x's and y's. So let's do a little practice with this. It will help with some numbers that we're familiar with. So, do I have shapes here? Yes. So I'm just going to take one of these shapes. I'm going to put it over here, and I don't know if I can fill it in and do all that yet. I don't think I have my fill in here. Okay, I don't. So I didn't call it up. So let me just cover it up with the heart. See if I can move that. Okay. So under the heart is a log, right? You see the log? Covering it up. Cover up your log. A log, my heart is 2. A log is an exponent. So this thing becomes an exponent. So I put it up in the air like that, and I don't know what either one of these things are yet until I move the heart. All right? I'm going to move the heart because I need to know what base, what number is being squared. Here's my exponent. A log is an exponent. So I move my heart a little bit, and I get to see what the base is, 3. So I can put a 3 right here. The base of the log and the base of the exponential function, if they're inverses of each other, must be the same. So what do you expect is going to be the input to my log function? You already know what the question mark is. What's the question mark going to be? 9, because 3 squared is 9. Okay. So see what it does? The log says, I can tell you what the exponent is that I raised 3 to get this answer. Because you would have originally put in a 2 and come out with a 9. You would have had the point 29 on your graph of your exponential function. Now you're putting a 9 into your log function and coming back to 2, the original exponent. So this is your input right here. This is your input. This is the output. So on your log function, it looks like this, the 0.92 on your log function. On your exponential function, it's 2, 9. They just take places switching back and forth. All right. Now let's cover up this heart over here, this part. So my heart now is feeling negative, which means if I'm an exponent and I'm a negative exponent, you have a negative exponent. Remember, a negative exponent just tells you, in fact, an exponent of -1 says, I'm just the reciprocal of whatever my base is. That's all it says, the reciprocal. So we have something raised to the negative power equals something else, which I'll call some box here. So this is my log function. So the output of my log function is -1. The input into my exponential function is -1. The output of my log is the exponent. There it is. Now, how do I know what my question mark is? I scoot this heart over to look for the little base. Ooh, it's 8. So it's 8 to the -1. So if I put 8, oops, that's not right. So if I say my base is 8 and my exponent's -1, my answer here is what? 1 over 8, 1 over 8. So my output here is 1 over 8. That is the input right here into my log function. So you see, there it is sitting right there. All right. So that's how you convert from a log to an equivalent exponential equation. I just want to show you something else that I think is really kind of cool. And this is how we used to teach logs. We used to go like this. Log base 3. And then your hope is to write that thing as 3 to some power. Can you write 9 as 3 to some power? What would it be? 9 is what? 9 equals 3 to what? 3 to the 2. So notice, this is what we just did a minute ago. When the base of your log and the base of your exponent are the same, these are inverses, so all you do is lift off the exponent. Just lift it off. Here's your answer. Here's your answer. Just lift it off. They undo each other. So how could I write this one? Log base 8 of 1/8. If I can write 1/8 as 8 to some power, which I can, 8 to the negative 1, these just are inverses of each other. My answer is my input, negative 1. So that's just another way to do it. I'm just showing you various ways. All right, now let's go the opposite. We start with our exponential equation, and let's turn it into an equivalent log equation. So what base will be on this log right here in A? What will the base be? 2, the same as the base right here, log base 2. The input into my log will be the output of my exponential. So the 8 sits right here, and 2 raised to the third power gives me 8, so my answer is the exponent. So that's how you rewrite those. Those two things mean exactly the same thing. Okay? Just like 5x is exactly the same thing as 10x divided by 2. They're exactly the same. They have the same meaning. Okay, someone want to help me with this one? Someone who's feeling confident or feeling like they can take a risk? Oh, James? Negative 2 equals log base 6 of 136. Yep. The log is just the exponent. That's all it is. Same base. The output is the input. All right. So now it's time to evaluate each of these logs. Two ways to do it. You can just simply rewrite it as an exponential and figure out the answer. So this would be 10. The answer to this is unknown. That's what you're trying to find out. So 10 to some power is equal to 100. And then you solve for the power, you know it's 2. So you can rewrite it as an exponential, and hopefully you're familiar with exponents. The other way you can do it is to rewrite it as log base 10 and write 100 as 10 to a power. 10 squared. You've composed a log function with its equivalent exponential function. You come right back to where you started, which is with this thing. You lift off the exponent. There's your 2 for your answer. Because this is asking, what do I raise 10 to get 10 to the second power? And you say, duh, second power, 2. All right. Now this one, I'm going to do it several different ways. 1 divided by 125 is 5 to the negative 3. Its answer is staring at you right now, right in the face. What's the answer? Negative 3. You just lift off the exponent because your bases are the same for your log and your exponential function. You're composing inverse functions. Or you could go like this. 5 to some power equals 1 over 125. And then to solve, you have to write this as 5 to a power. And there it is. So your question mark is equal to negative 3. 5 times 5 times 5 is 125, and you take the reciprocal. Now, this is the whole reason why we did the second preview exercise. This says 36 to what power, because we know whatever the answer here is going to be the exponent, gives me 6. 36 to what power gives me 6? 1/2, right, the square root. Okay, so now you're on your own. You got plenty of exercises to keep you busy. Please let me know if you have any questions. I'm expecting questions, so please ask them when you get to them.